Hello, hello. Do you hear me? No? Yo. Do you hear me now? Maybe even more louder? Okay, I'll speak like this. Or even louder. Yes. So, it's a pleasure to be here with you today. My name is Tomáš. I'm the camera guy. You could see throughout the whole day. I'm also a PhD student here in MRS Lab, and with my colleagues, I'm responsible for the, let's say, technical part of this summer school, for the practices and the Friday practice round with the experiments. So let me roll out the presentation. Hope this will work. Terrible. Of course, general effect. This usually works. Okay, backup solution. Great. So, throughout this talk, I will speak briefly about history, how we developed our platform from the year, let's say, 2012, but it will be very brief. Then I'll tell you something about our current control pipeline, the one which you can actually download and install, and the one which you will use during the practices. I'll also tell you about some technologies and software we use to deploy our software on the drones and to actually do the real-world experiments, because this experience is very different from simulating in MATLAB and similar tools. I'll tell you about our control stack, and of course, I'll summarize with the tasks for the practices. I'll tell you how to run the code, what the code should print out and plot, and I'll show you how the code which will run during the practices can be simulated using Gazebo Simulator, and hopefully we'll see some nice crashes of the drone in simulator, not in real life on Friday. So does this work? Great. So in 2012, development of a controller for a drone started like this, by plotting a PCB layout by hand, and then iteratively going through development, which resulted in this. This is like 2015-ish control board, which we developed for our tiny drones. This control board could do onboard logging, multi-UAV communication, onboard MPC controller, modal predictive controller, Kalman filtering, and all of those fancy stuff we are used to. However, it was embedded. It worked great until it didn't, let's say, fulfill all of our requirements. Maybe, will I be able to show the video? Okay, I'll show the video from the folder since my primary PDF viewer didn't work. Sorry for this. No, that's fine, that's fine. So in the time with the embedded controller, we were able to do stuff like this. So this is complete onboard control. This is thing you can see nowadays on every DJI platform. This is stabilized using optic flow, and it is controlled optimally to mitigate all the disturbances. It estimates the force which is being applied to the drone. It was fancy, but it had its own limitations. We did some nice experiments with it during that time. However, the platform died pretty soon, and the reason is simple. There are actually multiple reasons. The hardware was purpose-built, and it didn't scale well, and each iteration took like half a year to develop, so that's pretty difficult to work with. The software was embedded, so every time you needed to update the software, you needed a programmer, or let's say an interface for the microcontroller on board. We had some good results, but we needed to ditch this platform. As I said, it wasn't scalable. The bottlenecks were everywhere. One of them is right here. I was needed for pretty much every experiment that was being done with the platform, because only I was able to reprogram the software. So also you couldn't easily connect cameras, rangefinders. Everything was difficult, but it was nice. I loved the platform, but later my colleagues persuaded me to try robot operating system, which we did, and that's what you'll learn today and throughout the week, how to use that. So this ended like 2015-ish. Since then, the platform changed very drastically. And nowadays, everything is built around a computer. Martin already talked about that during his talk. We use off-the-shelf Intel NUC, but we are not limited to that. We use Odroid, Raspberry, some industry-based computer, whatever you want. But everything is connected to this computer. Sensors, RTK GPS, mutual UAV communication, cameras, grippers. Everything we need is connected to the high-level computer. The only thing which remained from the old times is the embedded stabilization. Those who work with drones probably know that. Everybody needs some kind of low-level stabilization like Pigshawk or DJI's NASA or KK2 board or there's plenty of those. We use Pigshawk, so it's somewhere here. But in our pipeline, it serves only a minor role. It stabilizes the drone using its IMU and fast feedback loop. But we don't actually change the code in it, we just buy it and use it. And hopefully we are not limited to this platform only. So nowadays, our control pipeline, from the control point of view, looks like this. On the right-hand side, we have the UAV plant. That's the drone with the propellers, motors, ESCs. Those are the electronic speed controllers for the motors. And around the plant, there is fast feedback loop enclosed, in our case, using the Pigshawk. The Pigshawk takes care of attitude rate stabilization. So attitude rate, that's the rate of change of the attitude angles, yaw, pitch, roll angles. So when we need to control those angles, we supply attitude rate reference to the Pigshawk, and the Pigshawk takes care of that. So let's say we want to rotate by 1 pi radians per second. We tell that to the Pigshawk, and Pigshawk just does that with the drone, and the drone flips and rotates. Everything which is gray, if you actually see the color, I'm not sure. Do you see the color? Probably not. This and this and this and this and this, everything which is supposed to be gray runs on the NUC, on the high-level Intel computer. So basically every part of our pipeline can be versioned very well because it's on a Linux-based system. It can be changed easily and it can be simulated easily. That's very important. The old platform, embedded platform, couldn't be simulated easily. This one can, as you will see very soon. So our pipeline, as I said, uses the Pigshawk as the attitude rate controller. Above that, we have something we call a state feedback. It's a feedback loop which stabilizes the drone and controls its position, velocity, and acceleration simultaneously. So this is a feedback which calculates control errors on position, velocity, and acceleration, and produces the desired attitude rate command for the Pigshawk. We have several of those controllers. Some of them are better for rapid flight and aggressive maneuvers, like the Lee's SO3 controller, 2013. Some of those are better for like poor sensor data, because they are robust, they can handle the poor sensor data, like MPC plus SO3 controller, and so on. So this is a state feedback controller. Above that, we have something which we call a tracker. Again, we have multiple trackers nowadays. Tracker is a reference generator. It generates the desired position, acceleration, and velocity for the drone 100 times per second. So the controllers have something to do. The controllers, they don't know where to go and how to get there. They need somebody to tell them the actual path through the space. So that's what trackers do. Trackers take a high-level reference, let's say, let's fly from 000 to 10,000. And this we call it go-to command, is then translated into a series of changes of position, velocity, and acceleration states throughout the time from point A to point B. That's what trackers do. Trackers can also do some pretty clever stuff. They can, for example, take care of mutual collisions between the drones, as in this case of this plot, the MPC tracker does. So the MPC tracker, in our case, can take care of mutual collisions. It actually solves a problem of disentangling the drone's future trajectories. I think Martin actually showed you something about this work. And of course, somewhere above the trackers, we have a mission planner. Mission planner can be anything from sensor-driven control node, which takes measurements from LiDARs and tells the drone where to fly. Mission planner can be offline, nonlinear MPC planner, which plans trajectories for multiple drones. It can be anything which outputs high-level commands, like go there or follow this path. So this is our pipeline, at least from the control point of view. And what I'm going to show you now, it's a rough reality which we deal with almost every day. That's how to translate this control point of view pipeline, something which you can test in MATLAB easily, how to translate this into a real-world working software which you can run on a drone and which you can be almost sure that it will not crash the drone. I'm not sure how it's in other fields of control, but in drone control, every mistake is obvious because the drone crashes, usually horribly. And since drones are expensive, we try to not crash them, we try to minimize the number of crashes. And it's rather long path for us. Just a small example, you might have seen this piece of code somewhere. This is a math code for Kalman Filter. It's almost in every other paper which uses Kalman Filter. If you program this in MATLAB, it's roughly 20 lines of code, 10 to 20 lines of code, and it works fine. In MATLAB, everything works fine if you follow the math. But if you want to actually program this into the drone and make sure it works well every time, you are dealing with easily 1,000 lines of C code or C++ code. And this factor of 100 is almost everywhere you go with transferring science and research from testing environments to practice. Another example is the SO3 controller I mentioned. If you read through the paper, you'll find out that it's basically those 2 lines of maths. And if you program it in MATLAB, it's like 10 lines of code, and it works fine. Also, the modular predictive control, if you have a solver in MATLAB, solving this quadratic program is like within 20 lines of code easily. But if you want to program it in the drone so it works every time and it directs properly to every input, 10,000 plus easily. And now try to maintain this and try to give it to other people to use it. It's hell. So there are things which you have to consider when you transfer research and testing from MATLAB to reality. There is just a brief list of those. For example, you should account for sensors disconnecting during the flight. That can happen. USB connectors can be disconnected during the flight. You, of course, should account for tuning of controllers. They can be poorly tuned and the drone can go crazy, but still you should be able to save the drone even when it goes crazy. Control theory can do that. So there is a place for detecting unusual states of the drone. Of course, even if the controller can flip the drone, you shouldn't allow it to flip the drone if the flight should be done in calm conditions and such. So our code has a lot of fail-safes in it. The simplest guide how to do fail-safe is here, like detect if you are going to crash, and if it's true, just don't crash. Of course, it's not that simple in reality, but it's necessary. If you're going to deploy your code and your platform in real world, and as we do, if you are going to fly days and days and days long, you are eventually gonna find all of those problems by your own, and if you don't think forward and anticipate those, it will be expensive. So, how we actually program the stuff? Somebody asked this question to Martin. Where's Martin? There, awesome. I'm not sure whether he answered, so I'll answer for him. We use ROS, Robot Operating System. It's a middleware library which can be used in C++ and Python. It integrates into Linux, actually into Ubuntu natively. It integrates into Linux's terminal, and it allows you to solve problematic stuff easily. And those problematic stuff are those ones which you really don't want to program by yourself. Inter-program communication, time synchronization, asynchronous execution of complicated pieces of code which might not even be related, like computer vision and control. Those really run on different math problems. ROS can help you with lots of sensor integration. Nowadays, manufacturers produce drivers which are directly developed for ROS. So basically, you buy a sensor and you go to the manufacturer's web page, and there is a link to download the ROS driver. So ROS just makes the life easier, and it allows us to develop the applications in such a way that it's actually scalable. And that's important. Our lab has something like 15 plus people who actively collaborate on our code, and it's important to allow them to work on their piece of code in an isolated environment in such a way that they can produce new versions and they will actually not break your stuff. So that's important, and thanks to ROS we can do that. ROS integrates into simulators, as you have heard, Gazebo and VREP. It's very easy to use. I'll show you in a minute. From the implementation point of view, the control platform I showed previously is totally different. The graph looks totally different. This is actually a terrible image. I'm not sure whether does it fit. We should maybe fix it a little bit. Is it better? No. Okay, back. Okay, let's focus on the bottom part first. The bottom part shows you how we use the sensor data. So let's say we have multiple sensors on the drone. We have RP LiDAR, which is a rotating LiDAR. We have Garmin rangefinder, which measures a height above ground. We have Pigshawk, which gives us the estimate from inertial measurement unit. We have Blue Fox camera, which we use for calculating the optic flow and thus the speed of the drone. And we use RealSense sensor, which gives us data for example, ORB-SLAM visual odometry. All of those sensors output their data into our so-called odometry node, which estimates the position of the drone in some frame of reference. We use different frames of references based on which sensor is currently used, so we can fluidly switch from GPS-based fusion to, let's say, RP LiDAR-based fusion. This can happen if you fly from outdoors to indoors, like from a field to a forest where GPS suddenly isn't applicable. Then the RP LiDAR can give us the good data. So odometry node, that's the one which fuses all the measurements together. On the other hand, there is the control pipeline. And this is actually the first time I'm presenting this part of pipeline to anybody. Normally, I just show it to a new student, and I spend like 3 hours talking to him and plotting data on paper. This is the first time I've actually put it on a presentation, so sorry if it's confusing. We have something which we call a control manager. This is just a piece of code which integrates all the controllers which we have and all the trajectory generators, a la trackers, which we have. The thing is, we can fluidly switch from any controller to any other controller during the flight, as well as switch from any tracker to any other tracker during the flight. This is very important if your flight is something else than just a static experiment in controlled conditions. When we fly outdoors and when we test some different sensors, it's important to be able to switch from, for example, SO3 controller, which allows rapid aggressive maneuvers, to MPC controller, which is robust and can deliver some good performance even when the odometry and centrifusion goes crazy. So the control manager, it supplies or it manages communication between the controllers and the trackers. It actually loads controllers as ROS plugins dynamically. So every one of you can actually program a controller using interface which I can give you, and you can dynamically plug it into our platform. You don't need to like mess with our code. You don't need to change anything which we created. You just plug it in, and it can be then used directly. The same accounts for the trackers, so you can actually program a tracker. You can give me the piece of code, and we can directly plug it in and run it even without changing our stuff. So the pipeline altogether looks like this. We have also some other managers. For example, gain manager is a manager which manages, that's a terrible word, gains for the SO3 controller. It's very important to be able to switch control gains. Those are the stuff that makes the controller stable, the numbers, to switch the gains on the fly based again on the type of flight which we are doing. Like we need aggressive maneuvers, but they don't need to be precise. Switch to lower, softer gains. We need slow flight, but very precise. We can switch to tighter gains, higher numbers. This can be done on the fly, as well as we have something which we call a constraint manager. This node handles dynamic constraints. This is the maximum velocity, acceleration, derivative of acceleration, which is jerk, then there is the snap. All of those dynamic constraints can be changed on the flight, and control manager takes care of telling every one of those trackers that the constraints changed. So you as a user can just call a command in a terminal or just run a service in your node, and you don't have to take care of which tracker is currently active. You can just say, okay, my maximum velocity is 2 meters per second because we just switched to, let's say, optic flow fusion. And we have something which we call a UAV manager. This is just a high-level node which takes care of automatic takeoff, landing, some safety routines as well. So this is the control pipeline from the software point of view. If you are interested in the fusion, Matěj Petrolík, my colleague, is actually responsible for this nowadays. I'm responsible for the control manager, controllers, trackers, and UAV manager, and gain manager, and constraint manager, and such. Optic flow is managed by Victor Walter. Then what else is here? I think this is all for this. We, of course, have much more. I just wanted to give you some condensed view of the pipeline. So, but when we deploy this, we need to use some other software as well. As some unnamed researcher told, every smith needs a hammer. We also need some tools to actually work with the robots. And throughout this talk, throughout the rest 15 minutes, you'll see me working with Linux terminal. Please don't be afraid of that. That's pretty normal to do. You'll see me working with something called Tmax, a terminal multiplexer. This is a program which allows us to run multiple subterminals in a Linux terminal. It's very important because when we are connected remotely to the drone, using this program, we can easily run multiple programs in a background, like if you open multiple tabs in a browser. You might see me using a Ranger file manager. It's pretty common in our lab. You might see me using a Vim editor. It's also pretty common in our lab. Don't be afraid. It's a normal modern editor. Sometimes you might see me using a terminal in Vim, in Tmax, in terminal. This is crazy. So, as I said, we use simulators. This is Gazebo. In this instance, there is a drone on a boom. There is a ball on a boom on a drone. We can add different modules and sensors to the drone dynamically, as I'll show you soon. Wojtaspurni actually made a pretty neat script which is called spawn. If you call spawn --help, you'll see all the modules and sensors which can be added to the drone just by appending the particular parameter to the command. This is all on our wiki. You don't have to write this down right now. Just know about this. It's pretty important. And now, this is the time for the live demo. I hope it will go well, because the first law of robotics says never give a robotic demo. So, first I'll show you how the simulation can be actually turned on. The stuff I'm gonna do right now, please don't repeat it on your laptop. We have a web page on Wiki which says, attention please, following commands are not meant to be issued manually. We usually script this, so you just press enter. But for the sake of completeness, I'll show you this line by line, but don't repeat this manually. Students come to me and they say, it doesn't work. I ask, have you read this line? No, why? Don't know. So, don't repeat this, just observe what happens. So I'll first run the simulation. It's a single ROS launch file which runs Gazebo, and it's ready to input or spawn a drone or multiple drones. So in Tmax, on the left-hand side, I create new tab, important. This can be done on the drone remotely as well. This is how we run our software on the drone. And I spawn a drone. So just by inputting spawn, I suppose you don't see this, by inputting spawn 1, that's the ID of the drone, --run, --delete, --enable rangefinder, I'll supposedly spawn a drone. So here you can see we have a drone somewhere there. Then I'll run all of the control software and all of the estimation software we have. That's another command. We all script this, don't have to type this manually usually. So our control software is running, and it's ready to take off. And as in the real world, first we need to tell our software that the drone is ready to fly. There's a safety check. So I'll call something which we call motors on, that's a service call. Now our software actually outputs data to the Pigshawk, and now we have to do 3 things. We have to arm the drone, as in the real world with the transmitter, normally, pilot does that. We have to switch the drone into the off-board mode, which is a mode where the drone listens to the computer and not to the remote controller. And then we need to take off, and that should be all. So let's arm the drone. Let's switch to the off-board mode, and let's take off. And I'm not sure whether you are able to see that, but the drone actually took off. So this is all that needs to be done to play with a single drone in a simulator. And now, since the drone is controlled using ROS, I can open a new terminal right here, and I can issue some control commands. Let's say we want to move the drone to position 001.5. That's X, Y, Z. So I issue the command in terminal, and the drone just flies there. We have services to fly the drone to a position, alter the position by relative coordinates. We have services for loading trajectories. Of course, we have a service for landing. So now I just landed the drone. I can also spawn 2 drones. I'll not do that manually. That's rather tedious, but I have a script for that. So we have a nice tool which is called Tmaxinator, which uses this kind of description language. It's called YAML, to define how the session in the terminal should look like. It's pretty easy to learn. If I run this script, it creates a terminal multiplexer session for me, with all those tabs already pre-filled with commands. And if we wait long enough, sorry, my laptop doesn't do a good job of handling the simulation, but if we'll wait long enough, a simulator will appear. I'm not pressing anything right now. A drone appears. We should have 2 drones, drone number 1 and drone number 2. I can switch between those. And in a minute, the drone will actually take off. Wow, the time flies by. So if I enlarge this, So we have two drones, as you can see, flying simultaneously. And as in the real world, the drone actually communicate. And they exchange their own positions and actually predicted future trajectories from our trackers. So what happens if I try to crash them? I shouldn't be able to, but let's try this. Also, we have an ROS visualizer here. This is a nifty tool which helps you plotting all of those data which the drone knows and which you can possibly produce in your nodes. So in here we have some arrows which signifies like current position and reference and whatever. So let me rearrange those windows, and I'll try to crash the drones in this way. I'll send drone number 1, which is the one on the left-hand side, to our favorite 00s. Now you can see the predicted trajectory from the tracker, which is basically the drone's future path, plotted in the ROS. So the drone flies to 00, and let's send the other drone to actually collide with this one, which will be x, y, it will be -20 in y. And in the same time, let's send the first drone to collide with this other drone. So that's like 20 in here. So, and if our system works well, you can see that the drone on the left tries to avoid the drone on the right. This is our mutual collision avoidance system. It's very handy when we are testing student work, multi-robot work on our drones. It happens often that student programs something which needs the drones to meet, and we just don't like this. So hopefully when we'll do the practices on Friday, this system will not be used, but it's there. So this is how our simulation works. You can play with it. We have a wiki which you can read through. On the seminars, I'll also give you a small cheat sheet. I have written like a 4-page notes with some commands which you don't have to remember, but you'll find them here. Hopefully this will help you to go rapidly through the practices. Now I'll quickly show you what you'll actually do in the practices. So let's have a problem. Scientists and researchers have their problems. So we have a problem that we have some points in 2D environment, some positions, which we want to access. And each position has a radius around it. In our case, it's 2 meters. It's a neighborhood. And we want to visit all the neighborhoods of all the positions as fast as possible. This is a variant of traveling salesman problem, in particular traveling salesman problem with neighborhoods, where we want to visit each point just once, and we are satisfied when we reach the neighborhood of the point. You'll solve this problem for 2 drones, so it will be multiple traveling salesman problem with neighborhoods. So a solution, very naive one, can look like this. This is a standard TSP programmed for 2 agents. It's not with neighborhoods. You can see that the paths go through the centers of the points. And in this case, those paths are just lines, segments between those points. It's not very optimal, but it works. When we account for the neighborhoods, you can see that, for example, this path just reaches the neighborhood and it turns to the other neighborhood. We can, of course, sample the trajectories and we can feed them to our trackers, and the drones would probably fly, but this is not fast. The drone practically stops in here to again accelerate in totally different direction. You can try this on the seminars. It will be slow. We can improve this solution by using a different model for the drone. This is using Dubbin's vehicle model, where the path is actually curved. It uses parts of circles as its trajectory. And this is where you'll start in your practices. So you'll get a code which does precisely this. It plans a decent trajectory, which is not terribly slow, but it doesn't deal with cleverly distributing the points between the 2 drones. As you can see, both drones fly almost all around the place, and they can even hit each other on this path. again, when we sample those trajectories, the sampling is already programmed for you. You don't have to do this. You'll basically be given a functional code. But if you sample the trajectories, you can see that the drone doesn't stop anywhere except for its start and finish location. So this is what you start with. So let's see how it looks. How much do I have? 10 minutes, maybe? Good. So let's so you'll be given a code which the core of it is written in Python, and for you who don't have our system installed, the code can run without ROS, without any particular big dependencies on its own. So when you are in the lectures or at your hotel, you can run the code on your laptop just using Python. And what it does, there is a script called planner py. By the way, everything I talk about is written in a manual, which will be given, again, printed out. So when I ran this piece of Python code, just as /python-py, it produces the plan, which I just showed you a few minutes ago. It also produces plots of the velocity and acceleration profiles. Oh, sorry, just velocity probably. So you can actually see how long it would take and how fast the vehicle goes. When you actually want to try this using ROS, as you'll do during the seminars, you'll go to, again, to the source codes for the task, and there is a node called MTSP state machine, which has a tmax folder in it with a test subfolder in it. Again, there is a start script. And I hope I don't have to press any other button. This should spawn the simulator. This should spawn 2 drones in the simulator. It should trigger the planner, and it should fly through the trajectories using the drones. So again, let's wait for the computer. So we have drone number 1, we have drone number 2. So sorry, I needed to trigger it. So now the drones created the plan using the same script I just ran a few minutes ago using pure Python. And hopefully the drones will take off. Drone number 1, drone number 2, they'll fly to the start points of the trajectory. And they'll follow their pre-computed paths. So drone number 2 goes here, drone number 1 goes here. And when the drone reaches the neighborhood is colored green, so you actually see what it does, whether it is successful. Don't think that the controllers are perfect. It might happen if you plan the trajectory poorly that the drone will not actually reach the neighborhood, even if you think it will. Imagine when I look at this neighborhood, imagine then the drone's controller isn't perfect and it might cut the corner. Then the neighborhood will not be visited. It's then up to you how much of a slack do you give the drone, how much of a reserve will you have on this particular situation. Again, one parameter in the code. So in there was, sorry I missed it, there was a situation where the drone wanted to collide. That's bad. We don't want collisions. So when the trajectory will be, when the flight will be finished, the system will produce a report on how much time did it take, how many neighborhoods did you actually reach, and whether the collision avoidance was necessary for fulfilling the experiment. So it will be finished soon. So I'll just move through this very quickly. So we can see here that there is one neighborhood which wasn't reached. That's this one. It's probably because the collision avoidance was triggered, so the drone didn't fly where it should fly. So now it's stopped. Actually, this drone has finished. This drone will finish very soon, right there. It's very slow on my computer. Normally it's like 2 times faster, but my simulator is on its knees. So now it's finished. And when we look back into the terminal, there is a tab called State Machine. The State Machine prints out that potential collision was detected, plus 10 seconds penalization. We missed 1 target, plus 5 seconds. The total score is 79. So this is what you will work with on your practice rounds. You'll get precisely this code with some functions which might be commented out or might not be actually implemented, and you will be playing with improving or how to improve this code to be actually much faster. In the end, those of you who will reach the best score will be more likely to have your code being actually tested on Friday on real drones. So if you want your code to run on real drones and to actually control the drones, try to push this total score down, and we'll watch over your shoulders and write down who's the best. But we can't promise that everyone's trajectories will be flown through, but the best score will probably be tried on the drones. So, what did I miss? You have seen this, we have seen this. As I said, we have a wiki. If you go to our repositories, you'll actually learn this on the seminars. We have a wiki which you can read through, learn how to control the platform. I'll hand out the cheat sheet again on the seminars, so don't be afraid that you have to memorize a lot of stuff. We want you to just play with the code, not to develop some new stuff and to be buried in C++. We just want you to play with it. So we'll give you as much ease as possible. Here are some links if you are interested. This presentation can be actually found on my GitHub, somewhere in here. So write this down if you are interested in going through it again. That's probably all from me for now. Thank you.
Yes, thank you, Tomáš. We have still 10 minutes even for questions. So ask if you have some question.
Yep.
Yes.
Can you pass it, please?
Yes, thanks for your presentation. Do you have any recommendations on whether to use C++ or Python in new projects? I would start with ROS.
It really depends on what we are doing. Those are just tools which are good for some stuff and not for some other stuff. So in our case, Python is awesome for prototyping. If you want to produce code quickly and test it quickly. It's also good for high-level stuff like machine learning. Probably computer vision might be, not sure. But Python is not good for real-time control because it's not statically typed, and you can easily try to set a string variable with like int, and you'll not reach this part of code. Sorry, if you don't reach this part of code during testing, you might encounter this error on the fly, and the code will just crash, and that's trouble. So use C++ in any kind of serious application where you need the code to run in real time on a drone or a robot. And if you care about not having the code crash just because you mistyped some variable, use C++ for that, and use Python for some quick testing. So for example, the code which you'll work with is Python, but it can be because it just plans a trajectory. And if it doesn't work, it will immediately stop, and you can like fix it even before taking off. But in case of controllers, if you have some strange problem in controller and it crashes during the flight, what the drone can do, like it can just crash. So it's a tool, use it for the right stuff. That's the only thing I can say.
Yeah, that's pretty much what I wanted to know, thanks.
Another question? Yes.
what is your opinion? What are the most severe limitations and drawbacks of ROS?
Drawbacks. Actually, honestly, it's hard to think about any nowadays. Of course, the learning curve is rather steep, but we try to mitigate it with manuals and wikis and such. And if you have a good student, he can work within a week pretty well. So that's probably not a drawback. Drawbacks. It's not lightweight, I would say. In our case, when the control pipeline runs, it produces roughly like 1,000 topics per second, and it can be too much for like ARM processors like Theodroid or Raspberry. So I would say it's not lightweight, but the benefits overweight this like greatly. So just buy a better computer and it will work well. So now I can't think about any drawbacks.
Thank you for the presentation. I would like to ask the both of you, what's your take on open source code? I mean, is your code going to be all open source, including the like everything?
Yeah, we are open, however, not yet open source, because it's work which somebody needs to do, and the one guy is probably me, and I'm the bottleneck again. So we are not protected of our code. We just haven't had the time to actually polish it well and put it out there so everybody can use it. But like, feel free to reuse it. Tell everybody about it. It's fine. I'm actually sorry that it's not on GitHub yet, but we are like really solving our own problems right now, and we don't feel that the system is ready for publishing yet. There is some work which needs to be done in the estimation, which can be really groundbreaking if we just make it open source and everybody starts to use it. So we are sort of afraid that it could break other people's stuff, but we are not protected of it. Like, we want to push it out, but the time probably isn't right yet, but it should be pretty soon.
Yeah, I will comment on that. I'm forcing them already exactly 1 year to publish the code, and I don't want to say that they are lazy, but they are too afraid. So maybe once you will be able to work with the system a bit more, we can make a voting at the end, and if you will agree with me that it's proper time for publishing the code, that it will be always not good enough, and there will be always something which could be improved, so we will publish it immediately. So thanks for that question. I have seen another.
Hi, thanks for your presentation. About the collision avoidance stuff, how do you like track the trajectory of the other robot? Do you know the pre-planned parts of the as a prior, or do you like track with the camera or stuff? In the actual field.
So was the question about how do we track the trajectories?
Of the other robots.
Of the other robots. How the robots know about each other's trajectories? So the mutual collision avoidance, which I just showed, it works only in GPS frame currently. It, of course, relies on the drones being localized within the same coordinate system, which means that even like the heading estimation has to be the same. In GPS-based system, the heading is defined by the magnetic north. So when this condition applies, we can exchange the drone's coordinates using Wi-Fi or other communication type. And since they are in the same frame of reference, they can account for the other drone's states. And moreover, they can account for the other drone's predictions. It's even more important to exchange where the drone's gonna be, not where they are now. Because if you fly like 8 meters per second and you want to mitigate a collision which possibly could happen like in 5 seconds, you have to exchange where the drones are gonna be. So we are actually sending drones predicted trajectories from the modal predictive tracker and that's what saves the drone. Not where the drone is, that's not enough, but where the drone's gonna be within the next 8 seconds. When the drones are not in the same frames of reference, then they are just objects in 3D space. So if you want to avoid the collision, you need onboard sensors, which you will detect the drone, or you need, for example, the UV light localization, which Victor is working on, so the drones can actually know about each other using cameras. But they can't just exchange their positions if one drone's origin is at that tree in the forest and the other drone's origin is that tree, for example.
So you're saying like you'll be like sending like 8 seconds, like roughly 8 seconds data of like the trajectory to the like broadcasting to the network.
Yes. Every drone sends its own 8-second prediction to every other drone, and each drone has a distributed system for detecting the collisions. We use a total ordering on the drones, so one drone has the highest priority, another drone has the lowest priority, and when a drone detects a collision with other drones, they actually change their altitude levels based on the priorities. That's what we use currently. So it also works only outside because they can ascend really high just because they avoid their collisions. This works only in open air.
Another question?
Hi, very good presentation. So I would like to ask, where are you running the Roastmaster exactly? Is on each drone? And then
Yes.
how do you exchange the information?
Yes, each drone runs its own Roastmaster, so they are independent. We use a Nimbro network, slightly modified Nimbro network, to actually communicate or exchange topics between the drones, but it works in a way that each drone basically has its own local publishers of topics from other drones, and there is a network layer which exchanges the binary data between the drones, but it's not a ROS-based communication. The ROS ends at each drone's network or system. So for the collision avoidance, we transmit roughly 40 3D points every 500 milliseconds. So it's like nothing. 2 hertz, 1 trajectory. So the bandwidth is negligible, but I don't have an estimate how much it is. It's designed to work even with like very bad connection, which it's most of the time actually.
Hi, Thomas. So I just wonder, since you guys are using Pigshawk, so are you doing anything with the lower level control? For example, for example, Pigshawk have their own module for optical flow. Then are you using their module or?
No, we actually use the Pigshawk as minimally as possible. So we don't change its own software. We utilize only its attitude controller, which is really the lowest possible level which you can use. So basically, our output to Pigshawk is 100 hertz, 4 numbers, yaw, pitch, roll, rate, and total thrust. And from Pigshawk, we read out the IMU data, the magnetometer, and the GPS. And that's all. We don't interface with it in any other way. Because we don't want to rely on it. Pigshawk can disappear. It's like platform as any other. Suddenly they can stop making it. B, it's not that reliable. We have mixed experiences with it. We have different versions of Pigshawk, and some of them are very bad. For example, they don't want you to they don't let you arm the drone if the Pigshawk thinks that something is wrong with a magnetometer, but we don't use a magnetometer primarily, so who cares? You want to fly, but the Pigshawk says, I will not arm. And even if you set all the knobs in Pigshawk right, there are situations where we just pull our hair out and say, why? We want to fly, and we have our own data for control, but Pigshawk thinks that its own estimator is like important to us, but it might not be, for example. So we don't want to be vendor locked to Pigshawk, and we don't use it more than necessary.
So when you said Pigshawk, you meant PX4 or Ardu Pilot?
We use PX4.
Okay. Okay.
Thank you for the presentation. You are using linear MPC and on the onboard computer, right? Is this linear MPC is enough for all the, for example, all the movement of the drone, agile movements? Did you try nonlinear?
So the question was whether the linear MPC is enough for the agile maneuvers. Throughout the history, I first used a classical linear MPC, even without constraints. That was the video with the tricopter. Of course, that used a linearized model in near hover state, and it wouldn't handle aggressive maneuvers well. But nowadays, we have two instances of MPC which runs on the drone. One is in so-called MPC tracker. That's the trajectory generator. That actually doesn't deal with the real rotational dynamics of the drone. It deals with the translational, like till the derivatives of the acceleration. So there is, it works with aggressive maneuvers, fine. And there is another MPC running below in the control level, and that's actually a hybrid of a linear modal predictive controller and a nonlinear state feedback, which is published in the LEAS 2013 SO3. It's not published yet. I merged those controllers together in a way where the MPC provides feed-forward acceleration, again using a linear model, and the nonlinear part of the SO3 handles the rotational stuff. And when you combine this, it can do aggressive maneuvers. It can easily recover from even like very, very weird position like upside down. And the MPC just generates acceleration and it's happy. So using this connection, it works well. Of course, if you would just use MPC to control the drone, the nonlinear MPC would be probably better for any type of agile maneuvers. I would say like beyond 40 degrees tilt, I suppose.
I have a quick question about the SLAM. You mentioned that you are using it, but you were using it just for odometry, or you actually use collaborative SLAM that all agents are cooperating and then you are doing your planning on partial maps? Or the map is known and then this is just for localization?
So currently our experience with onboard SLAM is only with a single drone. We yet do not share maps between the drones. That's something we need to do in the future. But nowadays we are able to fly indoors or in, as Martin said, in caves, tunnels, using SLAM based on LiDAR data, but just a single drone.
Thank you.
Last question. If there is no, I expect that you have enough information to attend practicals tomorrow and the day after tomorrow. Is it true? Or I don't know if it's Wednesday, Thursday. Tomorrow definitely. Yeah, so tomorrow the practical. And I have again extremely important information. Now we have the practicals in groups, but after that we are going to have again some beer. Yes, beer provided for you. So we have Vojta is our expert for beer. So we have 4 barrels waiting, or three barrels plus the one from the lunch. Yes. So probably 4 barrels. So don't be afraid of lines. This time there will be enough pipes. So this was the extremely important, and of course there is some barbecue already being prepared. So, but before we have the practicals. So there is a slight change in one of the rooms for the group C. So please follow this. This is the correct information. So I will ask now groups A and B, which is the swarms group. It should be 30 people. So please, these 30 people stay here. So who has group A and B, or who wants to participate in this group, please stay here. And then I will ask C, D, E, F, G, and H to go out and find my guys waiting for you with a letter. And then group I, who is not interested, you can choose from the list if you want now. And the same for other people who didn't vote it before. So thank you. Yeah, group F is here, so don't go. Group F, Tomáš is also here.